So here we are actually trying to figure out how we draw the shear force diagrams and the bending, or how to just calculate different values of shear force and bending moment at different points on any beam. And we had discussed that we will be primarily dealing with these what we call as cantilevers. We will be dealing with simply supported beams as of now. Then later on, we will have to deal with fixed beams. We have to deal with continuous beams. We have to deal with frames, and so on and so forth. But as of now, we are just trying to understand what actually happens when a structure is being loaded, how the structure or structural element responds. By it responds actually, the response is in terms of shear force and bending moment and axial forces as well. But axial forces, the value of, or the magnitude or the of the axial forces is quite low. So so we usually neglect the calculation of these normal forces. We don't take into account many a times these normal forces while analyzing any structure. So in our previous class, I guess we were actually checking the response of any cantilever, which has, I guess, 3 point loads at three different points. And then we saw how we can calculate its shear force and how we can calculate its bending moment diagram, right? So uh, in order to understand this shear force or bending moment diagram, we had already annotated the sign conventions, how we are actually how we will be dealing with the signs, or how we will be dealing with the orientation of bending moment, and and accordingly assign their positive and negative values. But that has to be uniform throughout the analysis of any structure. So we can go for a quick revision with regard to the science we already know about. We know about shear force. When we have a shear force, when we talk about shear force, we say shear force is positive when the element is sheared such that it tends to move in clockwise direction. Okay, shear force is such that on any part of an element, and we see that the left part of it is actually going upwards and the right one is going downwards, then the shear force is said to be positive. And if vice versa, that is when the left part is going downwards and the right part shear forces, because the direction here is which direction? It is anti-clockwise direction. Then we say this is negative shear. And when it goes in clockwise direction, we say it is positive shear. We say it is positive shear. And similarly, when we calculated different values of any cantilever, let's say we have this cantilever, and we saw that it has some forces, external forces being applied on some parts, on any part. Let's say that is P and Q. And in that sense, we saw that it will be having a positive shear force, right? Why positive? Because there is a reaction at the fixed end, and then this element will get shared in this direction, because there is a load P and Q. It will try to bend it in this direction, or it will try to share it. Actually, it's not bending what we are talking right now. It will try to share it in this way, and the end, that is the fixed end, will tend to give the reaction, or just to bring it in equilibrium, it will give an upward reaction. Therefore, we can say this shear force will be positive here. It will be similarly, shear force will be positive. And when we talk about bending moment, we know that as per the sign convention, we have seen that if the element of the beam is has bend in such a way such that concavity is upwards. That means it is sagging and the values will be positive. This is called as sagging movement. And we also know if it is hogging, then in that case, it will be negative. This is your hogging and sagging. Now here you can apply this sign convention. You can see that this beam will actually bend in hogging direction. Therefore, bending moment will be, your bending moment here will be negative. Okay, this was the case when we deal with simple cantilevers. Now that if we have or we have the same cantilever, but it has a, we have this cantilever again. Let's take the cantilever only, and we have a upward force of, let's say it is P and Q, and there is a reaction at the end. Now that we can also say that at this point, let's say this is point A and B. Now whenever we have to calculate the shear force at point A, shear force at point A, we have to calculate shear force at point A. We can choose either of the directions, right? We can choose one direction, wherein, or we will make another diagram, similar diagram, but the direction is opposite. Direction is opposite. That is, this is P, this is Q, and let's say this is your VB, and here again this is your V, let's say A, and here you have this point B. Now, what is the difference between the two? The difference will be certainly in drawing its shear force diagram, right? Difference will be certainly in drawing its shear force diagram. Here, for case 1, let's say this is your case 1 and this is your case 2. Whenever we have to calculate the shear force at point A, it will be certainly P plus Q minus VB. This will be your shear force. That means the amount of load that is coming from the upwards is positive. This is positive. This is positive, and the one which is going from bottom towards upwards, these are going downwards. The P and Q are going actually downwards. Downwards will be taken as positive. Downward force will be taken as positive, and upward force VB, it will be taken as negative. And similarly, when the case is of the opposite nature, that means it's fixed at point B and it's free at point A, then if you have to calculate your shear force, at point B now, the signs will change. Certainly, signs are going to change now because the directions have changed. Initially, the direction of VB was Initially, the direction of VB was anti-clockwise. Now the direction of VB has became clockwise. Therefore, you will have to change the signs as well. Now it will be simply equal to VB PA, minus P minus Q. Okay. When we talked about calculating movement at point B, this was shear force about A. Changing the support conditions, it has certainly changed the values. For example, okay, we will do a complete example on this. Uh, this was with regard to what? Shear force. This was with regard to shear force. Now, with regard to what we call as bending moment, what actually happens with bending moment? Does the same philosophy apply to bending moment also? We will see that. For example, Here again we have a cantilever. Fine, and it has been loaded. Now we are talking about bending moment. We are actually talking about simple bending moment, how we draw the bending moment diagrams. As we already know, it is hogging movement. It is simply hogging movement, and it will be positive. Sorry, hogging movement is negative. Hogging movement is your negative. That means here, while drawing its shear force and bending moment diagram, we need to understand where is hogging moment and where is sagging moment. And on the basis of that, what we treat sagging as positive and we treat hogging as negative. And then while we have to calculate the moments, here we can simply say movement due to every downward force. Movement due to every downward force is negative. Is negative. And movement due to every upward force is positive. Now you will say that shear force has changed when we change the direction. But how will movement remain same? I said movement due to every downward force. Movement due to every downward force. Every downward force means whether you are looking to the beam or you are calculating the shear force from going to left to right or from right to left. In both the cases, I say that movement due to every downward force is negative and movement due to every upward force is positive. I said that going from either of the direction, whether we go it from left to right or from right to left at any section, that will be it will be regardless of here the bending moment will be actually regardless of whether we are going, it will be regardless of whether we move from right to left or vice versa. Why is it so? Because, for example, we have seen that for any bending moment, let's say this is our central line, and we say that for any sagging bending moment diagram, which one is this is your movement, this is your movement. I say this is your sagging movement, right? This is your sagging movement. And I say this is positive, but at the same time, if you see that the left movement, this one, the left movement is actually in which direction? It is clockwise direction. It is clockwise direction towards the left. But at the same time, if I have a positive value of this left movement, which is clockwise movement, on the left seam, similarly, I will be having a positive value again. I will be having again a positive value of movement on the right hand side when it is moving in what? Anti-clockwise direction. On left hand side, it is clockwise, and on right hand side, it is anti-clockwise. I say both are positive. I said both are positive. But now here, when we are looking, let's say this is a beam, this is a simple beam. When I was looking at the point, let's say A point and the extreme end as B point, when I was looking or trying to calculate the movement at point A, I said that the positive is anti-clockwise and negative will be clockwise. Simple. Sorry, positive is clockwise, negative will be anti-clockwise. But when I move to the other direction, when I move to the other end, I said the things are vice versa. The things are completely opposite now. That is why in either of the directions. I said that every downward force is negative, and every downward force in either of the direction will be negative, and the movement due to every upward force. That means if, let's say, this is our beam, okay, and we have some, it's a simply supported beam and we have some load, and we need to calculate the shear force and bending moment diagram. And here, as we already know, that it is a sagging movement, it will sag like this, and it will be having a positive movement. It will be having a positive movement. What I give it in this picture, I said that every upward or downward force is your negative force. Whether you go from left to right or you go from left, it should have been opposite. Actually, it should have been opposite. But at the same time, if the movement at point A was clockwise positive, the same has become negative. The same has become negative, and the clockwise has become positive. Therefore, the signs have changed from going one point to the another point. That is why I had mentioned that it will be same for downward force and it will be same for the upward force. Now let's say we will do a problem wherein we can incorporate method of sectioning. Actually, how we do method of sectioning. Uh, I had already way. Uh, this is taking us a little more time, but I want you to understand it properly because this is going to help you a lot in future. Now, you already know that a shear force diagram is basically a diagram which shows the different values of shear force at different sections of the member, right? And bending moment diagram, again, same. It shows the value of different bending moments at various sections of the member, right? Now, one thing that we should take in consideration that while we are drawing the shear force diagram, we should make use of the point that the shear force is basically constant over the unloaded bay of the beam, because when we have uh, what we call as different loading on any beam, we actually calculate it at the points where we have loads. We don't calculate it in between. We say that it is constant from going one point to another. It won't change. Okay, it won't change. And then it is and it varies linearly when the loading is uniformly distributed, right? It varies linearly when we have a uniformly distributed load, and it basically changes negatively when we have concentrated loads across the positive direction of x. That means we usually take the loads perpendicular to the direction, perpendicular to the axis of the beam. So let's say we have this simple cantilever here. When we talk about axes, we have simple cantilever, and let's say it has been loaded by load W at point B, and here is your point A. Okay, this is a simple cantilever. Let's say this is our case first, and we'll try to understand or judge the things in a better perspective. So here, what is this? This is a simple cantilever. It has been fixed on one end, and it has a point load at the extreme end of the free end. Now, what I say, let's say it has a span of L. It has a span of L. It's fixed at A, and it is free at B, and it carries a load of W. Now, what we do, we basically will consider a section like we had done it in our previous class. We consider a section at distance x from free end. That means we have considered distance a section which is, let's say we will give the section name as xx dash, which is at a distance of x from that free end. You can actually check it on either of the side. You can either go from A towards the B, or you can go from B towards the A. It will absolutely depend upon you. Now, what we have to do, we have to draw it shear force diagram. Simple. Shear force at any point x. At any point, sorry, capital X, at any point x. Now, the shear force at any point x will be simply equal to how much? If load is how much? You have a load of W, right? You have a load of W, and between the values of B and X, between the values of B and capital X, what will be your shear force? You only have one external loading, which is W. Shear force will be if you have a load W at three end, it will have again a load W throughout. It will be a constant load W. Therefore, you can simply say it will be positive W. It will be positive W. Shear force will be positive W. Why positive? Remember, then you have to calculate your bending moment at point X again. And that will be now whatever load you have multiplied by the distance cross section, sorry, the lever arm, that will be W into X. But what will be the sign of W here when you are calculating the movement? It is hogging movement. It will be minus. Simple, nothing to do much. Hence, here we can simply say shear force will be actually constant because it does not depend upon distance. It does not depend upon distance. Therefore, you can say it will be simply W throughout the length of the beam. It will be positive W throughout the length of the beam. Positive. It will be W at this end, it will be W at this end. And now, when you have to draw the bending moment diagram, but here you can see it depends upon the value of what? Depends upon the value of x. Now x will increase, right? X will increase from going from B to A. If it was 1, it will go to 2, 3, 4, 5, and 6, and it will reach to the fixed end A. Therefore, it will linearly vary. It will linearly vary. At point, let's say this is the center line, and then at point A. And again, you know that the bending moment is negative because it is hogging. Then here you can simply say that the movement is linearly varying. Therefore, it will be maximum at which point? It will be maximum at point A, and it will vary up till point B, and it will be negative in direction. It will be negative in direction. Fine. Now, if we have to, why have I drawn the bending moment this way? Because I know when bending moment, I have to calculate the bending moment at x, whose value is minus wx. So when x is equal to 0, bending moment will be equal to, when x is 0, that means at point B, bending moment will be equal to 0. And when your x is equal to L, bending moment will be bending moment will be W cross L. That will be at this very point. This will be your W cross L movement at point A. This will be your movement at point A. Similarly, if you have to calculate now the rest of the problems, you can surely do yourself while placing different values. Now you can just do one case yourself, and that is, I'll show you a part of it, then you will do it yourself. We have a beam. Let's say we have already done such type of a beam. And now we will try to do it in terms of sectioning. Right, we will try to do it in terms of sectioning. Let's say we have this fixed end A, And then we have number of loads. We have load 1, let's say it is 400 Newton. We have another load 300 Newton. We have another load 800 Newton. And then we have one more load 500 Newton. And they are equidistant all, that is 0.5 meter. 0.5 meter, 0.5, 0.5, 0.5. Okay, total is 2 meter distance. Now I have to draw its shear force and bending moment diagram, right? For that, what I will do, I'll initially let's name them A, B, C, D, E, right? First of all, when I have to draw the shear force or the bending moment diagram, if I have to go from, if I will go from A to B, A towards B, then I should be knowing what? I should be knowing reaction, right? And I should be knowing the movement as well. Now that if I don't want to calculate it as of now, I want to come from this point. I want to come from point E towards B and draw it shear force diagram accordingly. So what will I do firstly? I'll firstly do, I'll consider a section X which is at a distance of X from point E. First part is, let's say, part D and E. DE. I'll try to see how will the shear force and bending moment vary between D and E. What will I do? Shear force at point X, at any point X, will be equal to, it will be simply equal to 500 Newton. It won't depend upon X. Shear force does not depend upon the distance or the what we called as lever arm. It does not depend upon that. But bending moment, when I talk about bending moment, it will be simply this 500. It will be constant throughout the point D, from point D to E. When I have to calculate its shear force diagram, let's make both of them at the same time. Uh, Here, when I have to calculate its shear force diagram, I have seen that the shear force at this very point is now positive 500. Go into positive direction, make a 500. This is your, how much? 500. It will be same from point D to point, from point E to point D. Right? Now, if I have to draw its bending moment diagram, again, at point X, I say it will be simply equal to minus times 500 minus, because it's hogging, times X. Okay? Now, I have to calculate different values at different points. I have 2 points. Point 1 is when X is equal to as 0. That means which point? Point E. Giving the value of bending moment at D, that will be equal to 0. That means at point D, it is simply 0 and direction would be negative. And at point when X is equal to as how much? 0.5. That means at point D. Here it is E. Sorry. Bending moment at E is 0. Now when X is equal to as 0.5, you will say bending moment at D is now equal to minus 500 multiplied by 0.25. That will be equal to minus 250 Newton meter. That means at point D now, we have a negative value of how much? 250. We have a negative value of 250. Similarly, when you have to calculate now movement at, yes,
और 0.25 क्यों?
oh sorry, it's 0.5. 0.5. Now, when you have to consider another section, that is which section? When you have to consider part D and C or CD part, then in that case, how will you draw your bending moment diagram? Then your value of X will change. and it will be when we are considering which now when we have to consider part CD again, we will consider one more part and we will say this is our section X, which is at a distance of X now from E. Part D, that is, we consider what? We consider a section. Where is that section? XX dash or YY dash, whatever you feel like, at a distance of X, at a distance of X from E, at a distance of X from E. And now we have to draw its shear force and bending moment diagram. Now, shear force, firstly, we will make the equation firstly. Shear force will equal to, what are the forces now? How many forces are between the point C and D, or between the point E and X? This is your point X. We have two loads. How many loads have we? We have plus 500 and then we have plus 800. That comes out to be how much? 1300 Newton. We have total shear force. We have 1300 shear force, but it is shear force between X, that is distance X from E. Now you have to draw the shear force diagram. Between C and D, that will be simply how much? 1300. It will be 1300 now. And you have to draw now the bending moment diagram. Now, bending moment, for that, bending moment for X, shear for X, firstly, movement between X, that will be equal to, firstly, what is the load? Load is minus 500 times X. X is the complete distance, right? And then minus 800 times. But now 800 is at what distance? 800 is actually at a distance where you have to leave the distance of D and E, that is 0.5. You want to know the bending moment between C and D. You are here to calculate the bending moment between C and D. But X is from which point? X is from point E. X is from point E. You have to deduct that distance. Therefore, it will be X minus 0.5. That is the distance which has been already calculated for bend calculation of its bending moment diagram. Okay. Therefore, you can here write down mx is equal to as minus 500 times x minus 800x minus 800 into 2.4, that will be 400. Therefore, you can say now your mx equation is minus 1300 x plus 400. Sorry, this is plus 400. This is your equation now for calculating bending movement between C and D. For calculating bending movement between C and D. Now, when we have the end conditions as when x is equal to as how much? Firstly, we have end condition when x is equal to as 0.5. We cannot say when x is equal to 0 because x has been calculated from point E. We want movement between C and D. C and D has a limit of when x is equal to 0.5. Then your movement will be how much? Your movement will be giving the value of 0.5. It will be minus 1300 into 0.5 plus 400. And movement will be calculated quickly minus 250. which you have already calculated as 250. Cross checked. You have checked when x is equal to 0.5. That means at point D, movement should be same. Movement is same whether we calculated it for E and D or we calculated it for D and C. Now, when you're at x is equal to as how much? 0.5 and 0.5, that is 1. Then your movement at point D now. Sorry, C. This was your movement at earlier at point D, the movement was 250 Newton meter. And at point C now, where x is equal to as 1, giving the values of 1, it will be 1300. Minus 1300 plus 400 will be simply 900. Minus 900 Newton meter. So you can go from this distance to this distance where you have a minus 900 Newton meter as bending moment. Okay. Now you have one more part. I think you will be able to calculate the movement yourself. Just do it quickly. Tell me the shear force at point between B and C and bending moment between B and C. Quickly. Bending moment between B and C. At any section between B and C. From E, we are calculating it from E. We came from left to right. So firstly, what will we have? We will be having a shear force. And shear force at point S X, that will be equal to simply what are the forces? We have force 500, we have 800 now, and we have 300 now. That will be simply equal to how much? 1600, right? We'll be having a shear force of 1600 Newton. And now from 1300 Newton, we will have to jump to 1600 Newton. This is now 1600 Newton. And when we have to calculate bending moment at any point x, firstly we have to calculate the equation. Now what will be the equation? In this third case, what we have done now, we are saying let's consider the section at a distance of x from E. In between what? B and C. It should be in between B and C. Just the one, the span in which we want to calculate the bending moment diagram. Now here we will be having a equation between B and C, and that equation will be firstly we have an extreme and lower 500 into complete x because it is at a distance of x distance. Now 800 minus 800, but distance is how much? It is simply x minus 0.5. We are leaving the distance which is beyond the point D. And then we have one more distance that is 300. Now it will be x minus 1. We will be having x minus 1. And giving the values, that means at x is equal to as how much now? When x is equal to as 1, we have two end conditions. That is when x is equal to as 1. And again, we have another when x is equal to as 1.5 meter. Because if you see, the point C is at a distance of 1 meter from E. That is why one extreme end is C, which is at a distance of 1 meter from E, and the Another extreme end is B, which is at a distance of 1.5 meter from end E. And giving the values, we will be able to calculate bending moment at point C, giving the value of x is equal to as 1. That has to come how much? It has to come 900 Newton, and it is equal to 900 Newton meter. And secondly, when your movement at C giving the value of x as 1.5 in the equation, it gives out to be 2700, sorry, it is 1700 Newton meter. That means now your another movement at point B is 1700 Newton meter. Now you are left with only movement at point A. Now giving all the values, again, you will be able to calculate the bending moment at point A. Will you be able to do it?
So और एक section करना है consider A and B.
Yes, you have another section. Now it is A and B. Now you have to consider one more section between, that is A and B.
Okay.
Now, firstly, you have to consider section between A, A and B from E. Mind that from E. So shear force will be certainly now, it will be 500 plus 300 plus 800 plus 400, and that will be equal to 2000. Simply, you can here now draw moment 2000. Sorry, shear force as 2000. Now your bending moment. Now your bending moment. And you can simply apply all the values and calculate the bending moment now. Calculate the moment equation. You will be having the moment at point B now as it will come out to be minus 1700 Newton meter, and then you will be having a moment at point A, and that comes out to be 2700 Newton meter. This is how you actually draw their shear force and bending moment diagram. 2700 Newton meter. This is your negative values, these are all positive values. You could have easily drawn, you could have easily checked what will be the moment at A. Simply taking summation of moment at A, summation of moment at A, and then calculating the values. And if you want to cross check it now, you can do it while checking it from, while going from point A to E. You will simply calculate what will be the movement at point A by just drawing it, by just calculating its movement, and that will come out to be 2700 Newton meter. Our time is almost about to end, so we will rejoin again. uniformly distributed load over the whole span, that is W per unit run. Now we have to draw it shear force and bending moment diagram. Again, what we will do here is we will simply consider what? Section X at a distance of X from point B, right? What we will do, we will consider a section X at a distance of X from B, and we will see what will be the shear force at X. Now your shear force at X, it will be simply equal to how much? Shear force at X when we have uniformly distributed load. It will be what? You have W per unit run times X. Now your shear force is dependent upon what? It has dependent, it is dependent upon the distance. In our previous case, shear force was not dependent upon the distance. But when you have a uniformly distributed load, how do you calculate the total load? You simply calculate it by saying that the total load will be simply your total load at point A will be how much? It will be W times L, right? It will be simply equal to W times L, because it is the load which is uniformly distributed having an intensity of W per unit meter or per unit mm per unit cm, whatever it is, whatever the unit of length is. Now here it will depend upon the distance. Okay. So here you have, but it will be again in positive direction. It is positive W into X now. Now we have to see what will be the bending moment. Now bending moment again at point X, in order to see what will be the equation, it will be simply equal to bending moment at any point X will be equal to minus W into X, that is the load. W times X multiplied by the centroidal distance, that will be at a half of X, right? Its centroid will be somewhere at the center, which is at a distance of X by 2. Or your bending moment will be here equal to Wx square by 2 minus times. That minus is because it is hogging. It will be in the negative direction. So the end conditions are now when, sorry,
x by 2 क्यों लिया?
x by 2 इसलिए लिया. Bending moment, what is bending moment? Bending moment is force multiplied by the distance, centroidal distance. Now how much is the total load? Load is your W times X. X is the distance, and this is your centroidal distance. How do we calculate bending moment? It is the product of what? The force and the distance from where it actually acts. This is your force and this is the distance. That is, it is minus Wx square by 2 when we are calculating what? When this was not the case when we were analyzing the case of point load or the concentrated load. But when you are dealing with what? Whenever you are dealing with uniformly distributed load, or whenever you are dealing with uniformly varying load, there the distance is the centroidal distance has to be multiplied. Okay, the load, this is your load, this is your shear force multiplied by distance, centroidal distance. So now you have end conditions. This is the equation for your calculation of bending moment. Now when at point x is equal to as 0, your shear force will be, shear force at x0 means shear force at B, that will be equal to W into 0, that will be equal to 0. Okay, and your movement, bending movement at point B, that means at point x is equal to s0, bending movement will be again equal to minus W into 0 square by 2, again 0. That means here you can say bending moment as well as shear force both are 0. Bending moment as well as shear force both are 0. Now second end condition is at when x is equal to as L. Your bending moment or your shear force when x is equal to as L means it is at point A. Shear at point A will be equal to W into X, that is L, that will be equal to as WL. And your movement at point A will be simply equal to minus times WL square by 2. Now here you can easily draw it shear force diagram. That means at point B shear force is 0 and at point A shear force is WL. This is your WL, positive shear force. Okay, now when I have to draw its bending moment diagram, I have calculated the bending moment diagram at point B to be 0. And at point A, how much is at point A? At point A, we have minus times WL square by 2. Now, this will not vary linearly. Will it vary linearly? Because we have WL square. W, whenever we have square, you already might be knowing, therefore you can say the variation is parabolic. It will vary now parabolically. That is why in previous class Zarka wanted to know how do we know that what varies linearly and what varies parabolically. When you have a square at the bending moment equation, it simply will tell you that the variation of this bending moment between any 2 points is actually parabolically. It is varying in a parabolic fashion. Parabolic variation. And now giving the different values to W will give you different values of bending moment at various different points. Okay. This was your second case. We can do one more case. Uh, let's say we have a case wherein we have this cantilever. It has a uniformly distributed load and it has a point load at the end also. That means the combination of both. Now, what will happen when this problem arises? Let's say it has a point load of W and then it has a small W per unit run as uniformly distributed load. Again, same procedure is same that we consider any section X at a distance of X from point B. Let's say this is point A, this is point B. Now, how will it vary? How can we actually calculate the shear force and bending moment at two different points? Now, when we have considered a point which is at a distance of x from B, firstly, what we have to calculate, this is your case third, we will have to calculate shear force at any point x. Let's say it is S. At any x, it will be simply equal to, firstly, you have what load? You have a point load, that means simply W. And then you have what? You have a uniformly distributed load, small w times x. This is your shear force at any point x. And then you can calculate your movement at any point x. That will be equal to, because of these two loads, now we have two loads. We have a uniformly distributed load, we have a point load. But the direction will be negative because it's hogging. So, firstly, your load is W. W, when you are talking about movement, it will be W times X. And your uniformly distributed load will be W times X multiplied by X by 2. This will be your movement equation. Movement is simply what? You will have to multiply the distance to the shear force that is there. Right? If this is the shear force equation, how is it different from a moment equation? You just have multiplied the distance, centroidal distance to the uniformly distributed load, and the linear distance to the point load. Simple, nothing new. So now when you have end conditions are at x0, what happens? And at x equal to L, when x is equal to as 0, that means at point B, your shear force at point B will be equal to what? When x is equal to 0, it will be equal to W. Shear force is not 0 now, keep in mind here. Shear force is not 0. When you have the point load or the concentrated point at the extreme end, then in that case you have seen that it will be having a shear force of W. And it will be having a movement of mx. Now putting the value of x is equal to 0, it will be having a 0 moment at point B. Now at point when x is equal to as L, your shear force at point A now will be equal to how much? Giving the value of x is equal to as L, that is equal to as W plus small w L. This will be your shear force at point A. And your bending moment at point A will be equal to, giving the value of x is equal to as L, will give you WL plus WL square by 2. Okay. Therefore, giving the values or drawing the shear force diagram, at point B, you can see the value is W, and at point A, it is W plus capital W plus small WL. It will vary linearly. Simple. This is your positive diagram. This is your shear force diagram. And then when you have to draw its bending moment diagram, again, at point B, it is 0, and at point A, it is this value. Minus times, or you don't have to mention minus times because we were already drawing this bending moment diagram in negative direction. Therefore, you can say it is WL plus WL square by 2. And it is again varying in parabolic fashion. Okay, it is varying in parabolic fashion. Now, for example, we have another case, last case. Then we will switch to simply supported beams. Now, let's say a case which we have already done. That is, we had a uniformly varying load, a triangular load. It is W per unit run, span of X. Okay, this is your point A and this is your point B. Okay. Now, again, when we have to draw it shear force and bending moment diagram, what we do is we consider any section X at a distance of X from point B, and we try to find out what actually happens when we have to draw it shear force and bending moment diagram. So this is your case 4. Firstly, we have to see what will be the shear force at any point X. We need to understand what will be the shear force at any point X. And for that, we need to see what will be the load intensity at this point. Load intensity. We need to see what will be the load intensity. For that, I have already told you we use similar triangle and we calculate this load as, if this is your capital W, which is at this point, you can say that capital W will be equal to Wx, that will be equal to L divided by X. and your Wx at the point x will be equal to capital W x by L. Okay, this will be bar per unit run, per unit meter, or we don't have a specified meter here. That is why we say per unit run. So this is actually here the intensity of the load at point X. And we also know that the total load acting for the distance between the point X A and X B will be now equal to what will be the total load? Because now that it is varying linearly. How will it vary? Can anybody tell me? What will be the shear force? Shear force here will be the simply area of load diagram. How do we calculate it? Shear force here? We calculate it as per the area of the load diagram. Area of load diagram. Whenever we have a uniformly distributed load and we need to calculate its shear force, in that case we see what is the area of the load diagram between what, between those points. Here we have between the point uh, B and X. We will see what is the area between the 2 points, and that will be simply equal to half of your base. How much is base? It's X into intensity into a perpendicular distance, and that is Wx by L. Now Wx by L, that is your Wx by L. So you can see that your shear force at any point X will be equal to Wx square by L. This is your
सर ये एक
shear
बार
force
रिपीट
at any.
करेंगे आप प्लीज?
A bit louder.
एक बार रिपीट करेंगे आप प्लीज?
Sure, sure. देखो, whenever we have to calculate the shear force for beams which have uniformly varying load. Now this, I had made this triangle. What does this triangle mean actually? This means, for example, it has a load intensity which is varying this way, like 1, 2, 3, 4, 5, 6, 7, 8. It is varying linearly from point A to B. Okay, and in that is why I had made this as a triangular load. Triangular means that the intensity of the load is actually varying from point B to A. So how do I calculate? How do I know now what will be the shear force? Now for that shear force, I say let's see the area of this triangle. I say let's see the area of this triangle or either of the triangle to calculate the actual shear force. I see the area of the triangle for which I have to calculate the shear force. Here, when I talk about a section X between X and B, this section, for calculating the shear force, the intensity at point, first of all, I should be having two things. I should be having the value of base, which is how much? X, and I should be having the height. I do not know the height. Now that I was knowing the height, I was knowing the height W at the end A, and I knew the total length L of the total of the whole triangle, and I also know the length or the span of this small triangle which is between X and B. I said that I'll calculate the intensity of the load at point X. This is your point X, and that came out to be Wx by L per unit run. And now that I have this triangle and I have to calculate the area of the load diagram. Simple triangle, half of base into altitude. I said half of base is x and altitude is how much? Altitude I have already calculated, that is Wx by L. Simple. Multiplying them will give me the value of Wx square by 2. This is the shear force at any point x. Is it clear now?
Yes sir. Wx square by 2L.
2 Wx square by 2L. No, this is half of base Wx square. This is Wx square by 2L.
ऐसा है.
This is your shear force at point X. Now I can give the different values of X. Now, before that, I'll see what will be the equation for your movement at any point x. I'm not talking about any area. Now, here again, what will be the movement? How will we calculate the movement? It will be simply area between area of low diagram. Area of low diagram between x and b, x and b, multiplied by distance of centroid. Distance of centroid, distance of centroid of the diagram, of the low diagram from x. Okay, from x. This is the distance of centroid from of this low diagram from x. Now you can give the different values, that is the end conditions, wherein you can say I want to know what is the value of movement and value of shear force at point A and B. Here I'm only concerned about 2 points, that is point A and point B. Now if I have to draw the shear force at B, that means when x is equal to as, when x is equal to as 0, shear force will be equal to, what is the equation for shear force? It was Wx square by 2L. Giving the value 0, it will be 0. And then when shear force at point A, that will give us the value of when x is equal to as L. When x is equal to as L, your shear force will be equal to WL square by twice L. That will be equal to how much? WL by 2. 1L will go. This was your shear force. Now, in order to calculate the bending moment diagram, I just have to multiply what? Centroidal distance of the lower diagram from x and calculate the value. Here again, uh, at x is equal to as 0, your movement at x will be equal to, if our x is 0, it will be simply equal to 0. And at x is equal to as L, when x is equal to as L, or before that I have to calculate the value of movement x. I guess I have not calculated the value of movement initially. Firstly, I want to know what is the movement at point x. I forgot that portion. Movement at x, that will be simply equal to, now distance multiplied by, it will be minus times wx square by 2is L, which is the shear force actually, or you can say it is the area of the lower diagram between x and b, multiplied by distance from x. Now from x, it is x is the value here. You, whenever you calculate the centroidal distance, you should always calculate it from the point of x, from the point of x, because here we already know that from the point of x it is 1 by 3 centroidal distance, and it is 2 by 3 from the end. So whenever we have to calculate the distance of centroid, we should calculate it from the point of x. Therefore you can say it will be equal to 1 by 3 of x, and your final moment equation will be minus times wx q by 6l. This is your movement at point x.
सर इससे पहले सेंट्रोइडल डिस्टेंस लेते थे ना x/2, जहाँ पे हमारे
That is same, that is again from the x, that is also from x. X by 2 is, it is the central point when we talk about uniformly distributed point. whenever you calculate your movement movement with regard to the uniformly varying load, the centroidal distance should always be, or whenever you calculate it from for uniformly distributed load also, the centroidal distance should be from x. Okay,
Okay, sir.
here again you we have calculated, in both the cases we have calculated it from x. Now this is the movement equation for this uniformly varying load. Now again, at x is equal to as 0, your movement at b will be equal to 0. When x is equal to as L, your movement at A will be equal to WL minus times cube divided by 6L. Okay, minus times divided by 6L. Now, one thing is here which you should remember, that I have given the value of L now, and it will now become what? WL square by 6, right? WL. Okay, this is your WL square by 6 at the end. But here you should see two things have happened. That is, when I was trying to see what will be the shear force or bending moment of the load, I saw that the equations for your shear force, which is this. This is your equation. This is your equation for shear force, and this is your equation for bending moment. These are the two equations. And I saw that for shear force, it was Wx square by 2L, shear force equation at any point x. I saw that this will actually vary in which fashion? This will be having a parabolic curve. This will have parabolic curve. And for x cube, it will be having a cubic curve. It will vary cubically, and shear force will vary parabolically. So we now, while we are drawing the shear force or bending moment diagram, at point B I saw the shear force is 0, being in positive direction, and at the end point I saw that the shear force will be WL by 2, but it will vary in which direction? Parabolically. Because I have seen that at any point x, which was somewhere here, at any point x, the equation came out to be Wx square by twice L. That means it is a parabolic equation. And when I have to draw the bending moment diagram, again, it will be in negative direction. And at point A and at point B, sorry, it was 0. And at the end point A, it came out to be WL square by 6. It came out to be WL. But at any point X, it has varied now. Now it has a deep curve. For cubic, we have a deep curve, and that equation was Wx cube by 6L. And this has basically varied in a cubic fashion. It is a cubic curve. And here, this is your parabolic curve. This is your cubic curve, and this is your parabolic curve. I hope you have understood why I make different types of curves while drawing the shear force and bending moment diagram. We usually have either linear curve or parabolic curve or cubic curve, which we will come across in future when we are drawing the shear force and bending moment diagrams.
तो हमें कौन सी इक्वेशन कंसिडर करनी होती है ग्राफ्स ड्रॉ करने के लिए? एक्सट्रीम पॉइंट्स की इक्वेशन या फिर
Now,
जो हम
at any you have to see firstly here what you have to draw. You have seen bending moment firstly at any point. What is movement at x? Movement at x or shear force at x? It is actually equation which gives you the equation to calculate the bending moment at different points. Then you give the end condition that I want to know bending moment at point x is equal to 0. It could be when x is equal to 1, it could be when x is equal to 2, depending upon the spans of your beam. But what you asked for, how do we know where what equation is actually there for which we should consider the bending moment diagram? It is actually the moment equation without giving the different values. Here I had given the end conditions as when x is equal to 0 and l. That was the last point or the extreme end where we have to calculate the moment. But before that we had actually calculated the equation for
ओके
shear
सर
force and for bending moment. And for that equation, you have to see whether that's parabolic, that is varying in parabolic fashion, that is varying in cubic fashion, that is varying in linear fashion, and accordingly, you have to draw the shear force and bending moment diagrams.
ओके सर
Okay?
जी सर we have to consider the general equation.
Yes, yes, yes. These are the end values in that we give, but we have to see what are the equations that are actually to be considered there.
Okay sir.
Okay. Okay, then enough for today. Sure for tomorrow's timing, but I'll let you know in the morning what will be the timing, because I'm actually I have to go to university tomorrow. Maybe most probably if I go to university, then either early morning or late in the evening.
So if it is
Okay.
early morning, would you please inform us?
Huh, louder.
If it will be in the early morning, तो आप आज शाम को ही inform कर दीजिएगा please.
No, I cannot inform him sham ko. I can inform you early morning, tomorrow early morning.
So early morning
Because I
means
will get the
9
confirmation
a.m.
in the morning whether I have to visit university or not.
So around 9 a.m.
Okay, let it be. I'll try if I can inform you in the today evening only. If not, then early morning.
Okay sir.